which is Leigh Lapworth from Rolls-Royce. Big hand for Leigh.
Thank you, Martin. Good morning. So I'm Leigh from Rolls-Royce. I run the Computational Sciences Group at Rolls-Royce, and we're responsible for bringing in high-performance computing systems into the company. I'll give you a bit of an overview of what we do as a company. I've entitled this Aerospace and the Cloud. The only slide I've got on the company is this one, just to say that you might think of us as an aerospace company. Actually, we do a lot of stuff that's non-aerospace, but the biggest part of our business is still the civil aerospace. So defence aerospace, power systems, marine and nuclear. We're quite a diverse company today. We're also global, and that global aspect of the company is something I'll come back to when I talk about the export control, because that's one of the barriers that we have. So the talk is probably fairly peculiar. We have a big industry, we have some peculiarities. We make big gas turbine products that are covered by export control. So I've got a proposition I'm going to talk through. I'm going to put some things out there. Some of these are opinions. I'm interested in your answers to those. So the premise, there are numerous advantages to the cloud. I think we'll all agree that. We've seen some of those already. The rate of adoption for us is driven by regulatory compliance, security models, and then economic forecasting. And I'll do a little bit at the end on economic forecasting, because for me, in terms of how I move forward in terms of systems, either they're in-house or in the cloud, is about the economics. How do I forecast economics reliably to make those big business decisions they're going to commit budget for 5 years? Having said that, the company is quite a diverse company, so the adoption will depend on the type of workflow. So my area is simulation, which I'll talk about in a second. We also have a big services industry, as you might guess, and services is more than 50% of our revenue. Sorry, as opposed to the OEM. So just to give you a quick snapshot of Rolls-Royce, just some stats here. So we make products, they've got a 25-year life. They run for 40 million miles, and at any moment there was something like 400,000 people in the air with a Rolls-Royce engine under the wing, and every 2.5 seconds a plane either takes off or lands with a Rolls-Royce engine in it. So you can see the spread, you can see the geographic spread of where we're flying, where the hubs are. So cloud is an ideal platform for aggregating that data. So we've been in the cloud. There's a number of things that we've done in the cloud. I'll just touch on a couple of these. So we've got our HR systems in the cloud. May sound sort of not very impressive, but actually it's a pretty good system, and as somebody who operates that, it's a big improvement on where we were 2 or 3 years ago. So that's been up and running for 2 years, a big investment. I can't say whether that headline is true or not. It's not my area. More relevant to today, the top right there, we signed an alignment with Microsoft and then Singapore Airlines to do service data in the Azure platform. We signed that back in 2016. That's been developing. We've been doing various stuff in that arena, and we've been developing our in-house strategy. And then there were a couple of big announcements back end of last year, which are related. So first one in November, the alignment with Tata, and part of that agreement is to use their Teacup platform, their cloud universe, sitting on top of Azure. And then we then announced a big organisational launch called R2 Data Labs, which is then going to accelerate data innovation. So this is all about data analytics, BI in the cloud, all built on the Azure platform with alignment with Tata. So in the service industry, we're doing a huge amount in the cloud. It's growing rapidly, having a big business impact. That sells itself. The economics for that don't really come into play. So on simulation, which is, as I say, is my area, we've got a range of simulations that we do, and they fall into these broad 3 categories. Obviously, there's granularity underneath that. Starting at the left, so basic high-fidelity modelling. We want to understand the physics. We want to do the best models we can. Those are both computational fluid dynamics simulations, so high-resolution, unsteady simulations, and then a larger, very finely resolved turbulence model, turbulence simulation using large eddy simulation. So those are calculations where you always want to run a bigger mesh, you always want to run it for longer to make it converge, make sure it's converged, etc. But also we want to do operating points. So we don't do single calculations, we want to do operating maps. Next to that is the multidisciplinary design optimization, where we're now working more to component level. We want to simulate a component in with different disciplines, run lots of different scenarios that we would then stick into an optimizer. So we create an automated workflow and rapid optimizer around that. On the right, we then have effectively the direction of travel for many companies, which is virtual modelling. So how do we do a full product model? So for us, that would be a full gas turbine. We've done some very finger in the wind estimates of what that would cost. We reckon that's going to be 1 trillion degrees of freedom, that calculation, 1 trillion cells, 1 trillion degrees of freedom. It's probably, each calculation is probably going to consume at today's standard 1 billion core hours per calculation. So when we first did this, the sort of prevailing cost per core hour was about 10p per core hour. At that point, you can build a test facility for that much. So, but those costs are dropping rapidly. So on the design optimization, it is multidiscipline. So the engineers are doing this design, are trying to balance the weight, the stress, the life, dynamics and vibration, etc., etc. You can read what's there. So those become really very sophisticated, and they're very sophisticated on an in-house infrastructure as well. So these are difficult things to combine and run. It's a combination of commercial and bespoke codes. We've got quite a lot of our own bespoke codes that we run. Some of those will be big CFD type calculations that we develop our own, but some of them will be little correlations that we've had for 30 years against proprietary data and test data that only we have access to. So then you have, so components here are components of the workflow, not components of the engine. So you've got some that are sort of almost instantaneous. You probably won't be surprised to know there's a huge amount of Excel embedded in some of these things, which is a cause of concern. We've even got some of this stuff that will run on. We're combining Unix, Linux, and Windows platforms on some of these codes. Although we're trying to get the Unix codes finally out of these loops. So I say it's a very heterogeneous workflow in many senses of the word. So again, interested in people's experience and how would we migrate this into a cloud? Because in many ways, this is of those three use cases. This middle one is the one that's most amenable to the cloud. These are long-running things. We run them for some weeks, maybe sometimes many thousands of evaluations. Some of this, the stuff on the left there, we actually want that back in the morning. The engineer wants to put in maybe 2 or 3 runs of different designs, different operating conditions, and she wants them back the following morning. These big runs at the moment, we're looking at months. Even if we could run them, it's many months, but that will change with time. So this middle one, from a simulation point of view, is very much the one that we'd see going in most easily into the cloud in terms of an economic benefits. But actually, it's quite a very complicated thing to do. So again, if anybody's got any ideas on how to do that, come and find me afterwards. Let me say a little bit about export control. This is perhaps peculiar to aerospace industries, so may not be typical to other industries. So we're a global company. We work globally. We develop the code globally. So we've got a big research. So our engineering centres are the UK, mainland Europe, the US, and then we've recently opened an engineering centre in India. So they all work together. We try and move the work to where it's most appropriate, to where the skills are, where the engines are being developed. So US export control applies both to the destination and the nationality, and that the key thing there is the nationality. So even if you're a non-US national working in the US on a US project, then if you get access to US data, that's a deemed export, which is not the case with EU and UK export controls. which are primarily destination. You then have the two levels of export control. You've got the Department of Defence ITAR agreements, International Traffic in Arms regulations, and they are an inclusion list. So if you have got to be on a list of approved parties in order to have access to that data. If you're not on that list, you can't have it. The lower classification is then these export administration regulations, which generally come under a no license required. They're administered by the Commerce Department, and they're an exclusion list. So unless your name is on the exclusion list, then you can have access. So what does this mean? What does this mean for us in-house, and if we were going into the cloud? So data and software is covered. This is not just about physical products. So the export regulations apply to the software that is used to design those products. So if we have software systems that we're developing globally, and we have US nationals working on them, then that adds US export controls to our systems. When we started on this journey several years ago, we tried to keep a demarcation between what was UK and what was US and what was EU. Ultimately, it's like mixing drinks together. You can't keep track of it, particularly in software where people need to see the whole code. They perhaps change one line in one subroutine, and you can't keep track of that. So effectively, the export controls become what's the lowest common denominator, which in this case is the US export controls. So we need access controls in place. So what that means for the cloud, obviously server locations is important because that's geography. EU and US export control say the same thing. Then admin nationality is then the US thing. So as well as knowing where the servers are, we need to know what the nationality of the administrators are in order to access our data. And for many months, or so many years, but not quite that long, for some time, that has been one of the issues that we've had in adopting, even doing benchmarks in the cloud, those requirements. There are solutions emerging. There's the AWS ITAR compliant cloud in the US. There are other compliant data centers available. Encryption with the confidential cloud. There are solutions now emerging where if everything is encrypted and the keys are not known by the administrators, then that is an acceptable solution. So encryption, end-to-end encryption is really important to us. And again, if we go back to the workflows, if we say, okay, that solution in the cloud has got to be end-to-end encrypted in all of that workflow, that's potentially a big overhead in doing that in the cloud. And not only has it got to be end-to-end encrypted, the keys can only be accessible and known by Rolls-Royce people. The idea of then having a single key that spans that whole workflow is probably quite hard. So that's an area where a lot of interest. We have a lot of interest at the moment in terms of simulation. 5 minutes. Okay. Yeah. Oops. Where did I get to? Yeah. So I'm not going to say much about security because, in fact, these two solutions that are emerging at the bottom sort of cover security as well. So once you have to try and be compliant with export control, that enforces you to put the security systems in place. So just in the last 5 minutes then, so a little bit about the economic considerations. So won't be surprised that Rolls-Royce has got its own high-performance computing installations. We don't publish what they are or how big they are, so don't ask me to tell you. But in terms of making a business case, so a 5-year business case, we will go effectively, because of the size of investment, we will go to the board to say, give us the money for a 5-year upgrade in our HPC. Now we can predict that reasonably well. In fact, we can predict that very well. To within 10, we can predict the costs over 5 years to within 5, with about 10%. The business impact then of having a fixed asset is, if we don't size it properly, it'll be under capacity, and therefore we have queues and the cost impact of queuing. Now, I looked for some data on what is actually the business impact of queuing. If anybody's got some data on that, I'd be really interested to know that. Cloud, you sort of invert it. You're now trying to predict costs because, assuming that whatever you want in the cloud is available, what you need to control is cost. And capability is less closely related to total cost of operation. And you've got the benefits, you've got new hardware, so if I buy a system and keep it for 5 years, it's fixed hardware. In the cloud, new hardware is coming along more quickly, but as we've sort of heard already today, scalability and performance in the cloud doesn't generally match in-house performance, and that may change. And the business impact now is, again, you've still got under capacity. If you've set a cost limit that you can't go above, you may still hit the under capacity, but now there's cost overruns. You know, what is the impact of the business of cost overruns? I've tried to stimulate some thoughts. I've tried to take a purely hypothetical case, and this is not about doing a point comparison with. Some of you will easily be able to work out which system that is. So I've taken a system and tried to make the closest cloud equivalent I can find, and that's also difficult. You know, there is no real one-to-one comparison between an in-house system and a cloud system. Again, if you probably be able to work out which cloud provider I've used to give me that interconnection. But so that cloud, it's about 6 cents per core hour if you prepay. If you want it on demand, it's about 15 cents, and if you're prepared to wait, it's about 10 cents. So best case is we turn up and say I'd like to have 4 billion core hours for the next 5 years, please. I'll spread it over the next 5 years. This may well be a hostage to fortune, this slide. What I've tried to do, instead of projecting into...
exchange rates.
Exchange rates, yeah. So at the moment, and that 6 cents becomes 4.5p per core hour. I've projected backwards, and I've made some quite sweeping assumptions here. The academic system is a known system, and therefore its costs, certainly its capex is known. I'm not sure. I've had to guess its opex, and I've assumed that the opex grows at 5% per annum, which is perhaps an overestimate. Cloud, obviously, you know, we all expect cloud to get cheaper. So I've assumed at 20%, it gets cheaper 20% per annum, but projected that backwards, so it gets more expensive at 20% per annum going backwards. I've assumed 4 petabytes of fairly flat rate of £2 million per annum for storage, and then picked three initial cost rates. So the 4.5, 3.5 and 1p are here and project backwards. So the blue line is the advertised cost. The green line then is if we drop that by a penny. And the key there is actually that 1 pence difference back here gives me 90% of the total cost of this system over the 5 years. So a 1p difference. Now we're in an industry where we sell engines for many millions of pounds. So 1p, we're not used to thinking of 1p being a huge factor. If you're a pharmaceutical company selling drugs, then 1p is a big difference. So you know there are industries where are used to handling 1p difference. And then just to try and match the end point, if you go down to 1p per core hour here, that's how you match the end point. Lots of provisos, lots of apologies over that data. The message here is, for me, you know, wanting to bring in a new system at some point in the future, in the not too distant future, wanting to bring in a new system, how do I reconcile that I can predict that number to within 10% versus I've got that variability on the cloud? That's the message of this is not about doing a point comparison between one academic system and one cloud provider. It's about the economics. How do I, if I'm sat here and I can predict that number to within plus or minus 10%, and this variability, I've got that variability such that if I get it wrong, I could have bought my own system in 1 year. Last slide then, just summary. You know, these really 2 questions. What's the cost of queuing versus wait time? What happened when cloud allocations run out? And just to say at the end, I usually start with this. I have a computing strategy rather than a computer strategy to some extent. I'm agnostic about what computers deliver that capacity. It's computing I'm interested in. And cloud is a key element to that. Don't get me wrong. This is about, you know, how do I move to cloud in a way that I can make an economic forecast over 5 years that I can trust. Thank you.
Thank you very much. So